These are the notes for section 6.6 for logarithmic and exponential equations. So this section involves solving a bunch of various log and exponential equations using the properties that we learned in 6.5. When we learned how to, we looked at all the different properties that exist and so on and so forth. That'll help us to solve various types of log and exponential equations. So I'm gonna show you a bunch of them and discuss various techniques that are commonly used to solve these types of equations. And generally these techniques that I show you are going to be, they're going to be widely used for the majority of type of questions you'll see with these problems. So this first example, these first two examples, we'll look at some exponential examples on how to solve these kinds of equations, these log equations. So I want to solve the equation 4 times log of base 6 of x equals log of base 6 of 16. I want to solve that equation. So now I do have a little note here, and that is a note that you can use. There are various techniques, and you could have multiple choices to use for a given log equation. Generally, though, to get something out of a logarithm, you want to use an exponent. All right. So if you want to get rid of a log, and that's log, to get rid of a log, use base a. And I'll use a log of base a. I'll use a to the x, right? Because this undoes this, right? And then they're inverses of each other. Now you could also use the properties of logarithms to solve this equation. So if you notice in this equation, right, I have 4 times log base 6 of x. All right. So this x is going into the log function. This is log of base 6. So if you remember this property, right? If I have log of some base and the expression or the term that goes into the log function has a power of r, you could bring that r out front as a factor. So you have r times log base a of m, right? If you remember this property from the previous section. So you could use this property to solve this equation. But what we're going to do here is we're actually going to use this property from right to left, right? So this is what we have in the equation. If you look right here, we have a factor times the log of some base of a term. That's what we have here. So what I could do is I could bring that 4 back up to the exponent of this x. So I could rewrite the left side as log base 6 of x to the 4th power in the logarithmic function. And that equals log of base 6 of 16. All right. I just used this property right here. But I went right to left instead of left to right. I brought the 4 up here as a power, and I got x to the 4th in the logarithm. So now what I have, I could use this property now. If log of base a of m equals log of base a of n, then I could say, since these are the same logs with the same bases, then I could say that the expressions in the logs are equal to each other. That means m equals n. That was another property we had, right? And that's what I have here. I have a log of base 6, they're the same base, of expressions, right, in the logarithm. So since this is the case, I could say, therefore, x to the 4th equals 16. And this is just a simple equation that you know how to do. Just take the 4th root, right? So here you'll just take the 4th root of that. So the 4th root of x to the 4th. Now since this is a 4th root, I have to, and 4 is even, I have to use a plus or minus the 4th root of 16. Right? This isn't a square root, this is the 4th root. So you'll have x equals plus or minus the 4th root of 16, which is equal to, so if you do that in your calculator, if you go to math, and if you go down to right here at number 5, you'll see an x there with a square root symbol. This means you could choose the index to be whatever you want. In this case, I'm taking the 4th root. So before I type that, I want to type 4 in front of it. So let me type 4 and then go to math down to that. That means I've taken the 4th root of that result, which is 16, and that gives you 2, right? So I have plus or minus 2, right? Because 2 to the 4th power is 16, and negative 2 to the 4th power is also 16. So I have plus or minus 2. So these are the values for x. X equals plus or minus 2. But before you clearly define your solution set, you need to check your solutions. All right, that needs to be done. So before I clearly define my solution set, let me check my solution. So let me just go and say, now, here's the thing. Your calculator only, remember, your calculator only takes logs of base 10. This is a log of base 6. So I can't type it as is into my calculator. I have to represent this using the change of base formula. All right. So, you know, you could use this equation, or you could use this one. You could write this as, you know, if I use this one, which is perfectly fine. The only thing is I brought the 4 up in here. And I can use the change of base formula, and I can write this as ln of x to the 4th over ln of 6 equals ln of 16 over ln of 6. All right. So you'd have to type this equation in like this, using the change of base formula. Because your calculator doesn't use base 6, it uses base 10 for log. But your calculator does use ln. This is just for your calculator. So if I use my calculator, I just got to type this in. So let me store 2 in the x, and then let me type in the left side and the right side, and hopefully I get the same thing. They should be equal to each other. So ln, so let me put parentheses for the fraction, so ln of x to the 4th, that's the numerator, divided by ln of 6. So that gives me 1.547 ... Now let me type in the right. So ln, so parenthesis, ln of 16 close that off, close the numerator, divide it by denominator, ln of 6, close that off, and I get the same value. So that means 2 works. All right. So x equals 2 works. So that's part of the solution set. Now let me try negative 2. Now I'm going to, instead of typing it in, I could just hit second enter to bring up a previous entry. So if I hit second enter, I'll bring that up. If I hit second enter again, I can bring up that entry. Let me hit second enter again to get the one with x in it. When I hit enter there, boop, 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 I get that. Okay. And when I type in second enter, second enter, second enter, that's the right side, I get the same value. So negative 2 works as well. So that's my solution set. Both of those solutions work. So again, you have to type this. This is for your calculator to check in TI 84 or 83 calculator. You have to write it like this. But again, LOG and LN, even though this is for base E, this is the change of base formula that was given to you in the previous section's notes. All right. Now, another technique that's useful is that when you see multiple logs on one side of an equation, so if you see multiple logs, like several logs being added or subtracted, the idea is to combine into one log expression. Okay. So how do you do that? Well, you use those properties, right? Remember the properties on the previous section? The log of some base of the product equals the sum of the logs. So the log of some base of A plus the log of some base of B. And the log of some base of A divided by B equals, that's the log of the quotient, equals the difference of the logs. So log of some base of A minus the log of some base of B. So these properties are very useful for taking 2 logs and getting 1 log. All right. So I'm going to use the first property here because I have a sum of 2 logs. So I'm going to take this, I'm going to go from right to left again. I'm going to write the sum of logs as 1 log expression. So I'm going to take this equation. Now I have the log of base 5 of x plus 6 plus the log of base 5 of x plus 2. By using the first property, I can say this is log of base 5 of, so I'm going to put brackets, of the product of the first 2 terms. So it's going to be the product of x plus 6 and x plus 2. Yeah, going from here to there is using this property, and that still equals 1. Now that I have this, I could use this technique I showed you up here. To get something out of log, use E. To get rid of a log A, use A to the x. Right? I could use this note. Or if it's base E, you could use ln. All right? So technically that should be ln, but you get the idea. So since this is log of base 5, what I'm going to do is I'm going to raise both sides to the 5th power. Or I'm sorry, not to the 5th power. Raise both sides to the base of 5. That's what I meant to say. All right. So what that's going to look like is I'm going to raise the left side. So I'm going to have 5 to this power right here, which would be log of base 5 of bracket x plus 6 times x plus 2 equals, and now I'm going to raise this to a power with a base of 5. So that'd be 5 to the first power. Now what does that do? Well, by doing this, what's going to happen? If you notice right here, right, I have an exponent of base 5 and I have a log of base 5. They undo each other. They cancel each other out. So this term right here, the term that goes into the log function, just becomes by itself. So what I'm left with is x plus 6 times x plus 2 equals 5 to the first power, which is 5. And this is just a simple quadratic equation. So FOIL this out. So you're going to get x squared plus 2x plus 6x plus 12 equals 5. Subtract 5 from both sides. And then you get what? X squared plus 8x plus 7 equals 0. Okay, now this is just a simple quadratic equation, and it factors, right? So the factors are x and 1 and 7. And since they're both positive, both factors are positive. Which means x plus 1 equals 0, or x plus 7 equals 0, x equals negative 1, x equals negative 7. Okay, now I gotta check the solutions. So before I make my solution set. Now, in order to rewriting this in your calculator, you could rewrite this using the change of base formula as ln of x plus 6 times x plus 2 in the logarithm over ln of 5. You could do that in your calculator. There's nothing wrong with that. Just rewrite the left side as this and then type it in with x stored in there. And you could do that. And you could just check it the normal way. Or you could, if you look at the original equation, okay? Remember in the previous section, the domain of a logarithm is all positive numbers. So if I look at negative 1, right, and if I plug that in here, inside this logarithm, I'm going to have negative 1 plus 6, which is 5. That's okay. Negative 1 plus 2 is the log of 1. That's okay. So because I get some possible values there, that's okay. That's fine. I get a valid input into those log expressions. So negative 1 should work. Now, however, if you look at negative 7, right? If I plug negative 7 in here, what's negative 7 plus 6? That's negative 1. I'm going to have the log of negative 1. I can't take the log of a negative value. Same thing here. If I put negative 7 in here, I'm going to have log of negative 5. I can't have it there either. So when I plug in negative 7 here, I'm going to get an undefined result here. So negative 7 doesn't work. Negative 1 works because when you put that in, you'll get the log of a positive number in both of them. That's fine. But negative 7 doesn't work. Because if you plug that in, you're going to get the log of a negative number in both of them. So really, my solution set here is just -1. That's why you have to check your solutions. So, once you do that, and you can check it in your calculator if you want to, but if you like the old-fashioned way, but you'll get an error message when you check -7. Now, I want to make a warning message here. Warning. It is tempting to raise both sides of the base of 5 right off the bat. You might do this. You might be tempted to do that, but you can't do that. That's no good. Because if you did that, if you had done that, you would be improperly using these properties. You would be doing the cardinal sin of distributing a logarithm. You would be breaking algebra law, which is punishable by death. So don't do that. All right. So let's go on to the next page. So again, oh, my camera just likes to be funny. Don't know why it's doing that. All right, that's better. So again, I have multiple logs on the left side. So you want to get one log on each side. Make sure to get one log, or it doesn't matter if it's log or ln. All right. Whatever log you start off with is the one you're going to use. All right. Make sure to get one log or ln on both sides. So you're going to use those properties. All right. So this one right here, these two are going to combine. You're going to use that property of, the log of products equals the sum of the logs, right? So, but you're just going in the opposite order. So this will be, since I already have a sum, I'll write this as ln of the product of x and x minus 1. All right? Just use that property. And that equals ln of x plus 15. Now, I could distribute here. I could distribute that x in, but everything in here is stuck in there. I can't break that out or anything, but I could distribute the x within the natural log. That's fine. Or, since I have both sides, from here you have a choice, right? Just like on the previous page. You have a choice. This is kind of similar to the first problem we did, right? I have a log of something equals a log of something. Log of something equals a log of something. So I could either use this property, right? I could use this property right here, or I could do what I did down here, and I could raise both sides to the, I could take both sides of the base of the logarithm. Basically just raise both sides to the base of the logarithm. So either way works just fine. Since I'm working with ln, I'm going to the corresponding exponential function will be base e, right? So what I'm going to do is I'm going to raise both sides with base e. So e is going to be raised to this power, equals e raised to this power. And what happens there is the e and the ln cancel out. So you're left with x times x minus 1 equals x plus 15. And then from there, it's just a simple polynomial equation. Distribute the x squared minus x equals x plus 15. Combine like terms, so subtract x, subtract 15. So the x's cancel. So you're going to get what? On the left side, you're going to get x squared minus 2x minus 15 equals 0. Right. Now see if it factors. That's a quadratic. So x and x. The factors of 15 that give me 2 are 5 and 3. Negative 2x, so 5 must be negative, and 3 must be positive because 15 is negative. So x minus 5 equals 0. X plus 3 equals 0, which means x equals 5, and x equals negative 3. Don't forget to check. All right. Now, again, you might have to rewrite this, or you could just see if these things lead to negative values in here on the left or right. All right. Now, fortunately, this is base ln, so you don't have to convert it in your calculator. That's nice. That's really nice. So I could just check it in my I don't have to use the change of base formula here. That's pretty sweet. So let me check 5 first. So 5 store in x. Let me type in the left side. Let me go to the original equation. So ln of x, so natural log of x plus natural log of x minus 1. When I hit enter there, I get what? And I get 2.99 blah blah blah, right? Then we type in the right side. I should get the same value. So I get natural log of x plus 15. And I do. Alright, so that means 5 works. Beautiful. Try negative 3. Negative 3 store in x. Type in the left again. So you can type it in again or just do second enter. Second enter, second enter, there it is. Hit enter. Uh-oh! Non-real answers. You can see that if I put negative 3 in here, I'm going to get negative 4. And I have the natural log of negative 4 plus the natural log of negative 3. Both of them don't work. So negative 3 is no good. So my solution set is just 5. So yeah, whenever you're solving a logarithmic equation, the rule of thumb is to make sure you get, this is the rule of thumb. Make sure to get 1 log or ln on both sides. And then once you do that, you could use this property or you could raise both sides to the base of the logarithm, which will cancel out the logs. The exponential and the base will cancel out. Or you'll get a number on one side. It just depends what you have. So the majority of the logarithmic equations you'll see can easily be solved using those two techniques. Those are the rules of thumb you want to keep in mind. So when we're looking at exponential equations, well, you know, just like we did with logarithmic equations, right? How do you get rid of a logarithm? You take an exponent, right? Because that's the inverse. How do you get rid of an exponential? What's the inverse of an exponential? A logarithm. So it makes sense that if you have an exponential, to get something out of an exponent, you're going to take a log. Or you're going to take an ln, whatever one you have, whatever base your exponent is. To undo one, you do the inverse operation. Just like addition, the inverse operation of addition is subtraction. The inverse to multiplication is division. The inverse to an exponential is a log. And vice versa. Okay. So I have 2 to the 2x power equals 3. Now, you could, since the base of this exponent is base 2, you're probably thinking, all right, well, let me take log of base 2 of both sides. And you could do that perfectly fine. There's nothing wrong with that. However, since I can't use log of base 2 in my calculator, I can only use log of base 10 or the natural log in my calculator. In order to make it more convenient for myself, and for you, of course, is I'm going to take the natural log of both sides instead. And it's perfectly fine to do that because the natural log, or log log, have the same properties. You could do that. That's fine. The only time you have to use either log or ln is if when you have a logarithm and the specific logarithm is specified. But when you have an exponent, you could use ln or log of the specific base. Either way, you could pick your poison there. It's just a matter of flavor, really. Do you like vanilla or chocolate? I like vanilla. All right. So note, you could take log of base 2 of both sides. However, ln works fine as well, because the properties of both types of log functions are the same. So it doesn't really matter. So what I'll do here is I'll take the ln of both sides. So I'm going to take the ln of 2 to the 2x power, which equals ln of 3. Now, since I took the ln of both sides, what I could do is use the property that says I could bring this power out front as a factor. Because I have the log of something raised to a power, I could bring the power out front. So then what I have is 2x times the natural log of 2 equals the natural log of 3. Now these are just numbers right here. Ln of 2, this is not ln times 2. This is not ln times 3. This is the natural log of 2, natural log of 3. All right? Use your calculator. You can see that. These are just numbers. Ln of 2 is that number. Ln of 3 is that number. We just leave it like that because that's an exact form. So how would you solve this equation for x? Well, it's, since these are just numbers, right? Since ln of 2 and ln of 3 are just numbers, this is almost like doing this. If you think of it as this, you have to rethink you just have to retool your mind and look at it this way. I have 2x times a number equals a number. How do you solve this equation? Well, you could just divide both sides by 2 times 3. Cancel out the 2, cancel out the 3, cancel out the 2, cancel out the 3, and you're left with x equals 4 over 6, which is 2/3, right? That's what you would do if you had a number, if you had something like that. It's the similar process. You just have a number times x times a number equals a number. 2 times x times 3 equals 4. That's the same format. A number times x times a number equals a number. Don't be confused because you see ln of stuff or ln. You don't have. These are just numbers. We just leave them, instead of writing out the decimals, we just leave them like this because that's, it's easier to write. So to solve this for x, we divide both sides by 2 times the natural log of 2. The 2's cancel. The natural logs of 2's cancel. So I'm left with x equals ln of 3 over 2 times ln of 2. And that right there is just a number. This is just a number, all right? You could use your calculator. Now, the domain of an exponent, right, the domain of an exponential function is all real numbers. So it doesn't matter. I don't have to check an exponent, but I will anyway. I don't have to check the solution to an exponential equation. You should anyway, though. It's a good habit. You should, though. So, check. So ln of 3, parenthesis, ln of 3, close parenthesis, wait, divided by 2 times ln of 2. So parenthesis 2, second ln, sorry, I hit E by accident, ln of 2, close that off, close up the denominator, and it gives me that. So let me store that into x, and let me type in the left side of the original equation. So 2 to the 2x power gives me 3. Da-da-da-da. So that is my answer. So my solution set in exact form is ln of 3 over 2 times ln of 2. That's it. Okay. A few more examples. So you might remember this kind of equation. Solve 7 to the x minus 3 power equals 2 to the 2x plus 1 power. Now, if you remember when we did exponents in 6.4, one of the techniques we used was to rewrite the base as a bases as a common value, right? But we can't do that here. 7 and 2 don't have a common factor. So we have to use logarithms. Note, 7 and 2 don't have a common factor. So we cannot rewrite both sides with the same base. Therefore, we need logarithms. We need to take ln of both sides. So let's do that. So I'll have ln of the left side equals ln of the right side. So ln of 7 to the x minus 3 power, and that's quantity x minus 3. 2 to the 2x plus 1 power, and that's quantity 2x plus 1. So since I have a log of stuff to a power, I could bring the powers out front, like factors. So what I'll have is I'll have x minus 3 quantity times ln of 7 equals 2x plus 1 quantity times ln of 2. Okay. So my goal here is to solve for x. All right. So what I need to do here is I need to get the x's on one side and the numbers on the other. Now remember, this is ln, that's just a number. ln of 2 is just a number. So I could distribute this ln of 7 into the x, and I could do that if I want to, because I could multiply and I could distribute a number into a polynomial. You know that. It might be a weird number, but I could still distribute it, and that's what I'm going to do. So ln of 7 times x is ln of 7 times x, and ln of 7 times negative 3 is going to be minus 3 times ln of 7 equals, I just distributed the ln of 7 into both terms, and I can distribute the ln of 2 into the 2x and the 1. So now what I have is I have 2x times ln of 2 plus 1 times ln of 2 is just ln of 2. All right. I want to get the x's on one side, the numbers on the other. So these are the x terms right here. They're the ones with x in them. These are the ones without x in them. These are that's just a number. That's just a number. So I'm going to put this over here, and I'm going to put this over there. Basically, I'm going to swap these two. So I'm going to have minus 2x times ln of 2 from both sides. That'll get rid of this one. Then I'm going to add 3 times ln of 7 to both sides. And I'll get rid of this one. So what I'll be left with is ln of 7 times x minus 2x ln of 2 equals 3 times ln of 7 plus ln of 2. They have an x in common now. You know, the numbers are on the right, the terms with x's are on the left. So now they have a GCF of x. So I could factor out the x. All right. So when I factor an x out of here, I'll have ln of 7 minus 2 times the ln of 2. Now, I have an x times a number equals a number. You know, that's like 2x equals 3. How do you get that? Divide both sides by 2, and you get x equals 3/2. So same idea. Divide both sides by the number. ln of 7 minus 2 ln of 2. That drops out there. So I'm left with x equals 3 natural log of 7 plus ln of 2 all over ln of 7 minus 2 times the natural log of 2. That's my answer. Let's check it. Oh boy, logarithms galore, huh? You know, students get crazy when they see ln and stuff, and like they go nuts. I'm like, welcome to college algebra. Not too bad. All right. Parenthesis, numerator, 3 ln 7 plus ln of 2. That's the numerator. Divided by parenthesis ln of 7 minus 2 ln of 2. That's the denominator. That's the number, 11 points. So it's approximate, this number right here. This whole thing is approximately that. Let's store that into x. Okay, now let's type in both sides of the original equation. 7 to the x minus 3 power gives me that. 2 to the, cross your fingers, 2x plus 1 power. Hey, look at that. Gives me the same thing. Da-da-da-da. So that works. So my solution set is this big ugly thing. That's my solution set. It's just this big ugly number right here. So, you know, I know that these things can be a little confusing, but you know, it is what it is. They're not too bad, but as long as you take it one step at a time. You know, just take the natural log of both sides, bring the powers out front, distribute the ln's on both sides, get the x's on one side, get the numbers on the other side, and solve for x. Factor out the x and just divide, you know. Alright. Excuse me. So, remember the kind of equations that were quadratic in form, and when you used a substitution for u, you thought we were going to be done with that. So let me rewrite this. Remember, quadratics look like this. So I want to make a substitution, right? Remember that? So if I rewrite this as x squared minus 7 times e to the x minus 8 equals 0, right? I could rewrite the first term that way because that's just a power to a power, which is e to the 2x, right? 2 times x is e to the 2x. But by rewriting it this way, I have something squared minus a number times something minus a number. That's a quadratic, right? That's a quadratic, right? You can see that. Something squared minus a number times something minus a number. You could see a here would be 1, right? B here would be -7, and C here would be -8. Just for reference, right? But we're not gonna, we're not gonna use the quadratic formula or anything. We're gonna make the substitution. We're gonna sub u for e to the x. You probably forgot, because we haven't done this we haven't done this substitution for quadratics since chapter 1. But generally the u sub term is the middle term, the bx term. You might have to refer to your notes in chapter 1 for that a little bit. I forget which section it is in chapter 1, but that was a rule of thumb. So when I make this substitution, right, what I'm going to get is instead of u equals e to the x, I'm going to e to the x squared will be u squared. Minus 7 times e to the x will be minus 7u, minus 8. So this will just become u squared minus 7u minus 8 equals 0. That's a quadratic equation in terms of u. So factor it. U and U. 1 and 8. So -8 plus 1. Right? So this means u plus 1 equals 0. U minus 8 equals 0. U equals -1. U equals 8. But I'm not trying to solve for u, I'm trying to solve for x. Right? So now that I have this solved for, I'm going to replace u with e to the x, make the replacement. So I have e to the x equals -1. E to the x equals 8. How do I solve these equations for x? Take the natural log of both sides. You want to get rid of the e, so take ln. So let me come up here. So we could take ln of e to the x equals ln of -1. ln and e cancel out. You're just left with x equals natural log of -1. Uh-oh! What's wrong with that? I have the natural log of a negative number. No, that doesn't work. So that means, what does that mean about ln of natural 1? ln of, well, the natural log of 1, I meant to say, or -1. The natural log of -1. It doesn't work. So let me solve this one for x. So natural log of e to the x equals natural log of 8. Bring the x down front, right? You can bring the x out front. X times ln of e, they cancel each other out, equals ln of 8, which means x equals ln of 8. There's nothing wrong with that. So if I store that in my calculator, Store that into x. And that's what it's equal to, roughly. Type in the original equation. E to the 2x power, e to the 2x power, minus 7, e to the x power, minus 8, enter, and I get negative 3 e to the 12th. What does that mean? I should get 0, right? Well, what is this? Negative, that's actually scientific notation. Negative 3 e negative 12. That's calculator lingo for negative 3.0 times 10 to the negative 12th power, which means you move the decimal point to the left 12 times. So what you really have is a really small negative number. Very small negative number. And since it's so darn small, it's like, you know, it's negative 0.00000000 blah 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 12 times. That's so close to 0 that we could just say that it is equal to 0. So that is the solution. So my solution set is natural log of 8. Okay, you know, so those are some various types of log and exponential equations that you could see in a higher level math course, especially in calculus. That's the end of the video.